Thank you, Kai, and let me thank all the organizers for setting this nice workshop. I'll be talking about generalization bounds for uniformly stable algorithms and its joint work with Jan Vondrak. So let me start with sort of describing the cast of characters in this algorithms, what I'm even talking about. So sort of the basic setting we'll be looking at is kind of a standard setting of machine learning and statistics in general, in which we'll have some domain, which will denote by capital Z. You can think of those as being labeled examples, but this could be arbitrary domain. We'll have a data set that will denote by capital S, which consists of n points from the domain. We'll have some learning algorithm A, which maps a data set to some model in this set capital W. And we'll have a loss function that maps a model and the point to some non-negative value. So given this notation, we'll say that an algorithm A is uniformly stable or has uniform stability with parameter gamma with respect to this loss function if for all pairs of data sets which differ just in a single element and arbitrary point in the domain, the loss of the model output on the first of those data sets on the point Z and minus the loss of the algorithm output on the sort of neighboring data set on any point on that same point Z differ by at most gamma. So basically, the loss on any of the model output by the algorithm on any point, on arbitrary point in the domain, does not change much when you replace a single point in a data set. And this holds for all data sets and again for all points Z.
You don't limit the size of S, even if S is 1 point?
No, so here S is where we fix N. N will be fixed throughout the talk. So in some sense, this gamma is a function of N. So this is a very strong sort of notion of stability, but as we'll see, there are a number of very interesting algorithms which have this property. And our goal will be to understand what kind of generalization properties does this notion imply. Yes, Daniel?
So this means that if you change everything in the data set, you increase the loss function by most gamma times n.
That's right. In particular. And we'll see how that sort of affects the interplay between the range of the loss and the stability parameter in a moment. So we'll be interested in understanding how to derive bounds on generalization error from stability properties. And let me just define this formally. We'll also have some distribution or probability distribution P over the domain Z, which will be also fixed throughout this talk. And we'll think of our data set as being sampled IID from this distribution. So given this distribution, we can define the population loss for any model, which is just the expectation of the loss of a model on a point drawn randomly from this distribution P. And given a data set, we also can define the empirical loss of a model. Again, just the average, the mean of the losses on the points in the data set. And the quantity of interest for us will be the generalization error or gap, which is just the difference between the population loss of the model output by the algorithm on the data set S and the empirical loss of the model of the data set. And the reason sort of why this is non-trivial is because here again we are using the same data set to produce the model and also using it to estimate the loss. Okay, everything is standard so far. So our goal would be to say that if an algorithm satisfies stability, then we can obtain some kind of bounds on this variable, this gap, which depends on the data set S. But before we actually go and I'll show you the specific bounds we can prove, let me motivate the question why one would be even interested in understanding a generalization for uniformly stable algorithms. So, and perhaps the most interesting motivation comes from this simple and standard setting of stochastic convex optimization. And let me restrict here for the purposes of talk of some very particular and particularly simple setting of it, in which the set of models will be the unit ball in d dimensions. And our loss functions will be convex and one-Lipschitz in the in this parameter W, which is the model. And the goal is, as usual, is to minimize the expected loss, which is which is just the expectation with respect to this distribution of the loss, and we'll denote the optimum by L star. So of course we all know how to solve this problem. There is this the classical algorithm is the stochastic gradient descent, where you'll just do updates on gradient updates on every single point, and the the standard choice of rate would be something like 1 over square root of n, and you'll take the average of the iterates at the end. And we know that the guarantees for these algorithms that are at this point well known is that basically what the statement says is with high probability the true loss of the model that will be output will be no more than the optimum plus something on the order of 1 over square root n times the log square root of log 1 over delta. So this is nice, and we know that this is optimal. The biggest problem with this result is that in practice there are many other algorithms that are used. For example, we use batches, we make multiple passes over data, we often even do full gradient descent in some cases. However, the analysis that is used to obtain these guarantees really relies on the fact that we'll be using every point only once. And once you basically reuse data points, in most cases, we cannot say anything about generalization of guarantees of the algorithm. We basically don't know how to analyze the population loss of the algorithm, and unless we make some additional assumptions on the models. And the reason for this is that basically our favorite tool, the use of uniform convergence, no longer works in this setting. Specifically, if you actually wanted, so the standard way we would do it, we prove generalization bounds, is that we separate, we minimize the empirical loss, and then we argue that on some set of models or all possible solutions, empirical loss is close to the population loss, and that's so-called uniform convergence. However, in this setting, to ensure uniform convergence, one needs basically the error of the uniform convergence scales as square root of d over n. So it basically, one has to pay a factor d to get above the bounds that we have for stochastic gradient descent. One could maybe say that one doesn't really need uniform convergence over all models. It maybe suffices to prove only this convergence for the empirical minimizers. But even for empirical minimizers, one has to pay a factor in there which scales with the dimension d. So as a result, we cannot obtain the same kind of bounds via our standard approaches. And this has been observed first by Charles Schwartz and others, and the specific bounds are from my recent work. So given that we cannot use the standard analysis, what can we do? And it turns out that the best analysis, the best general tool that we have in this context to still analyze algorithms which reuse data points, as we often do in practice.
So what does it mean then? Perhaps I missed it. Might have.
There are some specific distributions for which there will be empirical minimizer which has such error. Here no, I don't know how to prove it with a square root. I believe that there should be one, but I don't know how to prove it. I don't know of anyone who does. But for uniform convergence, yes, there is a square root. So the most general technique which still allows one to analyze algorithms in this context, it turns out to be uniform stability. And by now there are two examples. The first one is kind of old, comes from the work of Bousquet and Eliseev, and which shows the following: if you add this kind of regularizing, I would call it stabilizing, strong term of to the empirical objective, and then minimize it either exactly or with very small error, then the solution of this will be stable, specifically for when this again in this setting where everything is where in the unit ball and convex and everything is convex von Lipschitz, we'll get our stability parameter will be something like 1 over lambda n. But introduction of this sort of additional term also introduces error. So now the minimization of the original objective will be not exact, but within lambda over 2. So in order to, one will basically have to trade off somehow the error and the stability when using this this approach. And another uniformly stable algorithm for this setting has been given in a work of Hart, Recht, and Zinger, who showed that basically gradient steps on smooth losses basically are stable, and there are various ways to instantiate their result. So for example, one way to instantiate it is to show that if you perform full gradient, t steps of full gradient with say a rate of 1 over square root of t, then the resulting algorithm first of all will have uniform stability with something like square root t over n, and will minimize, of course, sort of the more steps you make, the less stable you are. But the more steps you make, the better you optimize the empirical objective. So again, you will get a trade-off between how well you optimize and the stability parameter. And the reason why this trade-off is important is at the end of the day, we of course want to upper bound the generalization, the true loss, and the error on the true loss will be sort of the sum of error, our suboptimality on the empirical loss, plus something which depends on the stability, and sort of our bound will need to convert our stability bound to a generalization bound, and the better we can do that, the better we can map our stability to generalization error, the better guarantees we'll obtain for these algorithms. And indeed, all known generalization bounds for these algorithms rely on sort of these generalization bounds for uniformly stable algorithms. So let me now briefly show what's known about those. So for these purposes, we'll restrict the loss to have range 0, 1. And in this case, one can think of of the stability parameter as being in the range of 1 over n to 1. Indeed, if it doesn't make sense to think about stability being less than 1 over n, the range of the loss. Otherwise, you're not even using the whole range of your function. And if you want to think of some specific value of stability, you should think of the most interesting value for the purposes of analysis will be 1 over square root of n. So that's the stability that we'll have for our algorithms. And the question is what kind of generalization bounds we can get for this value of stability. So a result that has been known for now 40 years is that the expectation of the generalization error is at most, when the expectation over all data sets drawn ID from p to the n, is at most gamma. So the value is small in expectation, but that doesn't allow us to say anything, almost anything. Even we cannot convert it even to a low probability statement about how close it actually is in a specific data set. The reason for this is that this value can be negative as positive. We cannot even apply Markov inequality to say that with some constant probability it's at least some multiple of gamma. And of course we would like to say something stronger about generalization error, and that's kind of the reason why Bousquet and Eliseev introduced this notion of uniform stability. And what they have proved is that with probability at most delta, probability with probability at least 1 over delta, the generalization error is less than gamma times square root of n. So it's a high probability statement, but unfortunately you have to pay a factor of square root n in the rate. And what this implies, at least for our purposes, that it cannot be used for the interesting range of parameters where the stability is 1 over square root of n. So that which brings me to our result, and our result can be actually it's in exactly the same setting. We prove that the same result, but now instead of gamma times square root n, we prove a bound with basically square root of gamma. And it's kind of easy to see that in this range of parameters, it always dominates the previous bound. If you want to see it kind of pictorially, okay, so this is for n equals to 100, and that's the range of the parameter that we are interested in, of roughly 1 over square root of n. The previous bounds become already vacuous at this point. We get a bound that is at least gives something meaningful for all values of stability parameter gamma. It doesn't look as the same as on my screen, but whatever. So one natural question, of course, is this even the best bound that one can prove for generalization? And I actually think we give evidence that it's not the best bound. And actually we look at this by looking at the second moment of generalization error. We prove that the second moment is at most gamma squared plus 1 over n, which roughly, if you think of it, corresponds to the rate of gamma plus 1 over square root of n. So there is no square root of gamma, it's just gamma plus, but there has to be some kind of floor of 1 over square root of n. And it's actually easy to see that this is a tight result. That's the best one can hope. And from this result, one can already get some kind of low probability generalization results with the optimal rate by using the standard Chebyshev inequality. You'll get this rate of gamma plus 1 over square root of n. Of course, with the worst dependence on delta in this case. So again, it's easy to see that you have to pay at least gamma if you for stability, and 1 over square root of n is you get even for a fixed function that does not depend on the data.
Why is this worst dependence on delta? I mean,
Why is this worse? I mean, okay, we would like to, ideally would like to
log 1 over delta, right?
we would like to get a square root of log 1 over delta instead.
No, what is the reason for that?
Why? Because we only prove this bound for the second moment, this optimal. So okay, and again, the second moment also has been studied for almost 40 years, and the best previous bound was gamma plus 1 over n, so they didn't get the gamma square. In fact, sort of what was known for the second moment is what we now prove for with high probability. And here is again pictorial comparison. Well, whatever. This was the previous bound, and that's our bound. And again, in the interesting regime setting of parameters of roughly 1 over square root of n, we get stability with the rate of 1 over square root of n, whereas the previous bound basically gets 1 over 4th root of n. Okay, so that's all that I want to say about the statement of the result itself. Let me know if there are questions so far. So let me now briefly mention the implication of this for the problem of stochastic convex optimization for the algorithms that I've described. It's kind of easy to see that one gets, for both of those algorithms, one gets these kind of low probability generalization results with basically with the rate 1 over square root of n, but some kind of polynomial dependence on delta. If one wants for very small values of delta, it makes sense to go to the high probability results, but there the sort of the rate that one would get would be suboptimal, n to the 1/3. Although again, at least they're no longer vacuous, unlike previous results. And so basically, one gets stronger generation results in this setting. And let me mention one more application, which is kind of from a different domain, and also plug some other work of mine. And it comes from the context of so-called differentially private prediction. And these are algorithms, I skipped the motivation, but these are basically algorithms, randomized algorithms such that whose predictions are differentially private in the following sense. If you replace one element in the data set, the distribution over labels for any point on which you predict the model you predict will not change by much. Specifically, it will satisfy the standard definition of differential privacy, that sort of infinity divergence between the prediction of a model on point X when given data set S, and the same and prediction on the same point when given the neighboring data set. The divergence between these distributions, infinity divergence, will be at most epsilon. And it's easy to see that this definition, if the algorithm satisfies this definition, then for any loss function over labels, the expected loss will have uniform stability. I mean, it's kind of very similar definition here. It's for distribution, but it implies that that the expected loss will be stable. And this means that basically gives allows us to use the results on generalization to obtain a stronger generalization bound for algorithms which satisfy this property. And the reason I wanted to mention this application is that it also shows that this kind of framework of uniformly stable algorithms can be, first of all, used in the context of classification by looking. So normally a 0-1 loss would not be stable because it can only have two values, 0 and 1, and these are not stable. But if you look at randomized algorithms, you can now look at the expected loss, and there you can talk about stability. But of course, it will be stability for the expected loss. And secondly, even though in the context of classification, we do have uniform convergence whenever things are learnable, we might, for various reasons, want to use algorithms other than the empirical risk minimizer. There are other algorithms that we might want to analyze. And this framework, and that's exactly sort of the situation we had in this context. We had a new algorithm for which one could not apply uniform convergence bounds, but we were able to analyze it using this framework, even though, again, even though normally one would have a uniform convergence results in this setting. Yes, sir.
Are you assuming the loss is strongly convex on those two upper results?
So this is no strong convexity here. So we get the same bounds for both of the uniform stability results that I have mentioned. One of them adds a strongly convex term to make it stable. The other assumes a little bit of smoothness. So both have some additional. So the first one doesn't have any assumptions, but it adds a strongly convex regularizer. The second one does have a relatively weak assumption on smoothness. Okay, so that's all that I want to say about the results themselves. Let me now actually go to proofs. So in order to make the proof actually a little easier to describe, we'll go to even more general setting, which we'll refer to as data-dependent functions. Data-dependent function is basically any function which takes a data set and a single point and outputs a real value. You can think of, previously our data-dependent function was the loss of the model output on the data set S on point Z, but it could be any function which, again, depends on the data set and also a point. And we can define for this kind of data-dependent functions, we can define uniform stability in exactly the same way. So now basically, again, for any pair of data sets which differ in a single point and any value of the second parameter, the values are within gamma. So if you think of, so basically, if you think of the function which is output on any data set, when you change the data set, the function changes by at most gamma in infinity norm. So the functions which are output on neighboring data sets are closed within this parameter. I would like to prove something about the generalization error for such data-dependent functions, where, again, generalization error would be the expectation of this function output on S on a point drawn from this distribution minus the same expectation of the same function output on S when we average on the same data set. Makes sense? So we now like to prove something in this slightly more general context. And before going to our proof as a warm-up, let me briefly review the sort of the proofs of the simpler results, the well-known results that I have mentioned. So first we'll show that the expectation of the generalization error is at most gamma. And that's actually very simple. So let's first look at the expectation of the empirical error, which is just the expectation of the value of the function on a point chosen randomly from the data set. For each such evaluation, we know that stability allows us to upper bound it by the value of the same function when we replace the point at position I with some other point. So we can replace the point, and instead of using the same point, which is in the data set, we can replace it with a different point and add at most gamma. Now we can, so because this is true for any replacement with point z, this is also true when we replace the point at position I with a point z drawn randomly from the same distribution. So now just plugging this expression back into the expectation, we'll obtain that that this expectation of the empirical value is upper bounded by the expectation of this value with the replaced point, but the point with which you replace is chosen independently, plus gamma. If we look carefully at the sort of the parameters of this function, they're all independent. So these are, because we replaced point zi with some random and independent point, these n+1 points used here are all completely independent. They're all distributed as basically as p to the n+1. We can just rename them as the data set S and Z, which basically gives us that allows us to upper bound this empirical mean using the population value of the same function. So this is kind of the most basic and standard trick in converting stability to generalization bounds. So now that we see that the expectation is small, let's very quickly see why one can obtain some kind of high probability bounds. Okay, so this is what we have proved. So to get sort of a simple way to obtain high probability generalization bound is to observe that this function, this generalization gap or generalization error, as a function of data set S, has bounded differences. Basically, when you change just data set from S to S prime, this generalization error can change by at most 2 gamma plus 1 over n. And the reason for this, again, is very simple. So generalization gap has two parts, has the empirical, has the true mean, which when we replace a data set, because the function changes in infinity norm by at most gamma, its true mean can also change by at most gamma. If we look at the empirical part, again, there the change of the data set replaces both the function and the points on which this function is evaluated. So we have to pay gamma for the change of the function, and also because we replace one of the points, we'll have to pay at most 1 over n when we replace one of the points, and that's because the range of the function is of the loss is at most 0, 1. So replacing a single point can change it in the mean, can change it by at most 1 over n. So all in all, this implies that generalization error can change by at most 2 gamma plus 1 over n. So we can just apply the standard McDiarmid's inequality to get that the probability that this generalization error is greater or equal than its mean plus this bounded difference times roughly square root n log 1 over delta is at most delta. And we know that the mean is small. The mean is just at most gamma. So we get the result of Bousquet and Delizeev via this simple analysis. And then, again, you can see where exactly the square root n factors come from. So now let's get to our proof. And it's sort of, first of all, let me mention that it's based on ideas that have been developed in the context of analyzing generalization properties of differential privacy that was first done in the context of adaptive data analysis by Nissim Stemmer and Vitaly Stemmer, Nissim Stemmer, Smith, Steinke, and Ullman. And the technique, sort of based on the following simple observation, it's much easier to use these kind of stability, it's much easier to use this stability when analyzing the expected value of generalization error. Therefore, as a first step, these techniques use the following lemma. That's a very simple kind of exercise in probability. If you, for any, we denote by Q any probability distribution over reals, then for any such distribution, a probability that the value will be greater or equal than twice the expectation of the maximum over m independent copies of the same random variable is at most roughly 1 over m. So it basically says that the probability that roughly the expectation of the maximum of m independent copies is roughly 1 over m percentile. Just doesn't say anything else, but the nice thing here is that now we can upper bound the sort of the tail probability by analyzing the expectation of the variable that we are interested in, expectation of the maximum over m independent copies plus 0. Does the lemma make sense? So how would what would we need to use this to prove our result? We would need to basically create m independent copies of our generalization error, and to do this, we'll draw not just a single data set. We'll draw m independent data sets as 1 through Sm for m, which is roughly again 1 over delta, and our goal will be to bound the expectation of the maximum of these generalization errors on these m data sets. Well, there needs to be a 0, but I'll remove it just to make it a little cleaner. So how can one bound? Let's try to bound this expectation of the maximum of generalization error. So we can first look at the empirical part of this generalization error, which is again, which would be equal to expectation over the empirical value of the function on the data set L, where L is the index where the generalization error is the largest, the maximum of the generalization errors. And we'd like to do our standard trick of replacing. Yes.
I just don't understand
The basic lemma?
Yeah, I think, is it that V is greater than the maximum rather than the expectation of the maximum?
V is greater than the expectation of the maximum.
Oh, okay.
So this is all inside the probability over m independent copies.
Oh, okay.
It's
Yeah.
anyway. So we would like to understand how close the empirical mean on the partition with the largest generalization error is how close it is to the true mean of this function when we choose the partition with the largest generalization error. And we'd like to do it by using our favorite trick where we replace the one of the points in the data set with a fresh point. So, and if we do it, we know that if we replace one of the points in the data set with a fresh point, we know that the empirical mean will not change by much. That's sort of what stability gives us. The problem, however, once we change a single point in the data set, the data set with the larger generalization error might also change, might jump to a completely different data set. So as a result, this quantity is not stable, and we cannot just do the same trick. Basically, the problem is that, okay, so we cannot argue about closeness of these two quantities because the maximum is not stable. So how will we solve it? Actually, I guess it's pretty obvious. We'll want to stabilize the maximum. And to do this, we'll do it kind of via now sort of standard exponential mechanism, which is just a kind of exponential sampling, first introduced in this context, introduced by McSherry and Talvar in 2007. And basically what it does, it samples, instead of outputting just the maximum, it samples an index randomly with probability proportional to e to the sum alpha, which is some parameter that we'll choose later, times the value. So in this case, the value will be the generalization error at partition or data set with index j. So what do we know about this? This kind of way to pick the largest element or an element. We know that it's stable. I mean, in fact, it's known that it's stable in a very strong sense. It's differentially private, which means that whenever we replace any of the data points here, we know that the value of this, the value of generalization error changes by at most 2 gamma plus 1 over n, which we proved in our warm-up exercise, plus this factor alpha. I mean, it's easy to see that the probability of outputting any index j can change by at most e to this to the power of this parameter. And if we just plug it into sort of the same trick, we'll now again we can look at the expectation of the empirical value of the algorithm while choosing the index using this exponential sampling. We'll have to pay this factor of e to this parameter minus 1 because of the change in the probability. The probability of outputting every index can change by at most this value. Plus we'll pay gamma as before, just for the change in value. And again, the important part that is on this side, we'll obtain the expectation of the over the data sets, the choice of the index using this exponential sampling of the true mean of the function. So basically, after stabilizing the maximum, we can now relate the empirical to the true value. And the other important properties that we need is that this exponential sampling is actually close to the true the maximum, and that's just basically comes from sort of relatively easy to prove fact that it kind of implements a softmax. So the expectation, I mean, again, it holds in general for any values, but in this case for our generalization error, the expected value of this generalization error when we pick it using this exponential sampling is at least the actual maximum plus ln m over alpha. So now, okay, so we know that it's close to the true maximum, and we can also, for this soft maximum or stable maximum, we can bound this step from empirical to the population value. Just putting this together, we obtain that, again, the expectation of the maximum over m independent of this generation error over m, all the m partitions, is upper bound by this ln m over alpha from the approximate maximum plus this factor from the step to generalization error. Now by just picking the right alpha, which in this case is just ln m over gamma plus 1 over n, we get that this value, it's easy to see, is a square root of gamma plus 1 over n times ln 1 over delta. And if you recall, this is the value that we would like to plug into the right side of our high probability bound, and that's exactly the value that we were aiming for. So we get, instead of square root n times gamma, we get the square root of gamma plus 1 over n times ln 1 over delta. Yeah, and that's it. That's basically the proof. Again, we just stabilize the maximum and get a proof of the concentration equality. Let me know if there are any questions. Might be too fast for this talk, but it's really all the ideas are there. I mean, we also have some nice tricks to prove the second bound on the second moment, but those are a little more technical and harder to make interesting in a talk. So let me basically conclude. So as I wanted to show you that we now have a slightly better understanding of uniform stability, and we, perhaps most interestingly, have a new technique to prove bounds about it. There are many sort of open problems in this area, but sort of the most obvious here is that we still have a gap between upper and lower bounds for high probability in our high probability statement. So we don't really know the answer. And sort of it would be kind of interesting to understand which of these high probability generation bounds can be obtained under weaker notions of stability, not just uniform, but maybe some bounds and moments and so on. let me know if you have any questions.
Thank you. I was a bit confused at the beginning about your non-uniformity, the availability when there's non-uniform. So the setup of is different, and you're talking all the time about binary prediction. But the non-availability when there's non-uniformity is not in the setup of binary prediction.
So the setting that I described was general, not just binary prediction, and the result is this difference between uniform convergence is not for it's not for the binary prediction. It's for general stochastic convex optimization, which which is more general. If we know that we're solving binary classification via RM, then we are good. And for some other settings like squared regression with squared loss, we'll have it, but not in general.
Okay, thank you, Vitaly, again.